Alright, so in today's video we are going to make the notion or the concept of limit more rigorous. Okay, we already have seen what limit is roughly or somewhat vaguely, but we have a pretty good idea of what it is actually. For example, when we say something like this, we know what this means. It means that when we bring x close to 2, then 2x is close to 4. That's the most vague way of saying this, what this thing is. A more rigorous way of saying the same thing is that as x gets closer and closer to 2, 2x gets closer and closer to 4. But still, it's not as rigorous as we can possibly be. It is still somewhat vague because it has this adjective close. Close means how close. When we just simply say close, that is not mathematical enough. That is just simply a way of saying that something is close to something else. Now, the notion here is that we know one more thing about limits is that I have said it again and again, and let me again say it, that when we write a statement like this, we actually are not considering this possibility. In fact, this possibility has nothing to do with the limit. To express this in words, I can say this sentence: the limit of 2x as x approaches 2 has to do with what happens around 2, not at 2. Okay, what happens at 2? We of course know what happens at 2. At 2, 2x becomes equal to 4. But that actually has nothing to do with the limit. Let me give you another example to illustrate this point. We also have come across this limit somewhere. Now, here at least you can say what happens when x is 2, what happens to the function. The function takes the value 4. But in spite of that, what we are saying is that the limit or the fact that this limit is 4 actually has nothing to do with the function being 4 at 2. Okay, it's a separate fact that yes, it becomes equal to the value of the function at that point, but that's something else. The limit itself has nothing to do with what happens at the point where you are considering the limit, and that fact is it's brought out more clearly by this second limit. Unlike this function actually is not even defined at x equal to 0, but still the limit exists and it is 1. So this shows that what happens at 0 actually has no bearing on the limit at all, but what happens around 0 is what matters. Around 0, close to 0. So far what we have said in justifying such limits is that as x becomes closer and closer to 0, without being equal to 0 of course, because we have to take into account such situations, then the functional values get closer and closer to 1. But now the question comes, how close? And in quantifying this how close, we will end up having a more rigorous definition of the concept of limit itself. Okay, so let us see what we mean by this how close and how we can possibly quantify this phrase how close here. So this section is about target values and formal definitions of limit. We will see what target value means, and here we have this is how the section starts. keeping outputs near target values. Now, before we study this example, I can at least say what is going on here. Keeping outputs near target values. Here the target value is 1, and as you are bringing x nearer and nearer to 0, your sin x over x value is also changing, so those are the output values. We want to keep the output values close to 1. So that's why the heading looks like this. How? By keeping the input values x close to 0. Now in this example we are going to make these things much more clear. So let's now see what the example is saying. So in the example we see one function, and that function is f of x equal to 2x minus 1. And we want to control the output values of this function so that the output values must lie within 2 units from this point, y not equal to 7. And that is the point that you get when you put x not equal to 4 in the function. But in order to achieve this thing, you somehow have to say what x should be. That is, how close to x not equal to 4 must we hold the input x to be sure that the output lies within 2 units of that point. In other words, if we express this thing mathematically, then we have this. We want this to happen. The output value at x is 2x minus 1. Its distance from 7, that is this, should be not more than 2 units. In fact, it should be less than 2. In order to have this, what should we do to x? Let us solve this inequality for x. This is equivalent to 2x minus 8, its absolute value being less than 2. And we know that this inequality, because it involves absolute value, is itself equivalent to these inequalities. Okay. Now what we can do is, you can divide throughout by 2. That will give you this equivalent inequality. And I say equivalent because just like you can divide these inequalities by 2 to get this new set of inequalities, which are this. You can also go from here to there by multiplying throughout by 2, dividing by 2, multiplying by 2, because these numbers are positive, so the inequalities do not change direction from by the laws of inequalities. These inequalities in turn are equivalent to this one. So we now have an answer to this query. That is, how close must we hold x to the point 4 so that the output values are within 2 units from 7. We should choose x in such a way that it is within 1 unit from 4. Okay. If we can do this, then the output values do not stray from 7 by more than 2 units. So what have we achieved? See, if you just simply blindly look at this calculation, then that of course is nothing. We already know how to manipulate these inequalities. But what is it saying? It is saying that in order to make my output close to 7, how close? This kind of close. my input should be close to 1. How close? This kind of close. So here you see that how close phrase that we keep using in the informal definition of limit has somehow been quantified here using inequalities to some extent. But now we are going to explore this even more in this next example. And in fact, before going to the next example, let us just for once see what is going on here in a figure on the plane of the graph paper or wherever you may want to draw it. So what is going on is this. If you draw the graph of this linear function, it's a linear function because x is appearing in the first power. Then what do you get actually? So this is your x-axis and say this is your y-axis. We of course are not going to measure actual things and see what actually how the graph looks, but we are going to just see what it is that we can say from here without being too careful about drawing the graph. That is, we just merely draw the graph so that it's accurate enough to serve our purpose. We just need to understand. You see, I have drawn the graph like this because you can see one thing, that this is going to give us a straight line, right? And the straight line has slope 2. So I have drawn it somewhat steeply. Slope 2. Slope 1 gives you a line that makes an angle 45 degree with both the axes, both the positive axes. So this has to be more than that. So in that sense, I have drawn it like this. What else you can see is that if you put x equal to 0, then you should get y equal to -1. So that's why it should pass through this point 0, -1. Okay, so roughly I have drawn this graph. And also we know that since it's a linear function, the graph is going to be a straight line. Okay. Now, here is the thing. Say this is your point 4, and what we see here is that we have to choose those points x such that they satisfy this inequality. Now this inequality is actually equivalent to what? Of course it's equivalent to this, but you can also see that if you add 4 throughout, then this same set of inequalities become equivalent to this, x lying strictly between 3 and 5. So suppose this is 3 on this side and on that side this is 5. Now here's the thing. If you draw a vertical line through 4, then that line meets this point at some point. In fact, that point is where you have the pair 4, 7, because the function is 2x minus 1. And if you draw the horizontal line correspondingly, which passes through this point, then that is your 7. Okay. And if you similarly do these things for 3 and 5, then you are going to get these points. Well, 7, so 2 units on this side is 5 and 2 units above 7 gives you 9. In fact, you can see that if you put x equal to 3 here, you are going to get 5, and if you put x equal to 5 here, you will get 9. So that means you can see here in the figure itself what the example is asking. The example asks us to keep the functional values within this open interval so that their distances from whatever these output values are, the output values of course will lie on the y-axis, their distance from 7, whether they be above 7 or below 7, all of those distances are less than 2, and this much is 2, that much is also 2. For this to happen, the input values x must not stray from 4 on either side by an amount greater than 1. Okay, it must be within this interval. This much is 1 and that length is also equal to 1. So that means the question which asks whether this can be done, whether we can keep the outputs controlled in such a way that they are lying within a distance 2 from the point 7, and the answer is yes. We can do so by controlling the input in this manner. Okay, so that's why controlling the outputs by controlling the inputs. Now let's see a similar example, but this one is somewhat more practical. Example 2. Why the stripes or the markings on a one-liter kitchen measuring cup about a millimeter wide. The reason for that, you may know this if you use such measuring cups often, that there are markings on those. Because it's a measuring cup, there will be markings. The markings go like this, small horizontal bars, and some thing is written there also. Now those markings are separated by a gap of about 1 millimeter. That is, two consecutive marks like that have a gap of about 1 millimeter between them. Why? And it's also for measuring a 1 liter amount of water or whatever it is with that cup. So the thing here is that, of course, the cup is a right circular cylinder, right? It is something like this. I mean, if we forget the actual shape of the cup, I should not say shape, but the outer things, that is a handle for grabbing it, if we just ignore those things, then it is just like this. Okay, it has a base that is a circle and it goes like this. So it's a right circular cylinder whose base radius, or the radius of this horizontal cross section, is 6 centimeter. Okay, that's how these things are manufactured, and on the body of the cup you have those markings. Okay, and this gap is 1 millimeter. The question is why? Now we already know how to measure the volume of a right circular cylinder. Say this radius is r, we know r is 6 centimeter, but just for the sake of writing a formula for the volume, let's just call it r for a moment. And say you have poured this much of water, say, so that the water makes a height h. That much water we have in the cup. Then the volume of water is given by pi r square h. It's just a simple thing, no? The area of the base times the height, that gives you the volume. Since the base is circular, its area is pi r square. So that means since r is 6, so this is 36 pi h. And because r is fixed, now the volume of the water is, it becomes a function of that height h. Now with all these things, here is the question. It's a kind of question, means it's a question. How closely, let me just write it down, okay. How closely must we measure h to measure 1 liter of water? Which equals, you may know this, 1000 cubic centimeter. In fact, that much volume is called 1 liter. Okay. So how closely must we measure h in order to measure 1 liter of water or 1000 cubic centimeter of water with an error of no more than 1%. Now 1% of this much becomes 10 cubic centimeter. Now you may wonder, why though? Can we not just simply pour exactly how much we needs to pour so that the height becomes that, it comes to that value, so that you precisely have 1000 cubic centimeter of water and hence you have 1 liter. And in fact, that is why you are using a measuring cup, right, in the first place. So what is the need for becoming so careful and checking for error? That's because this is real life, okay, this is reality. In reality, you are bound to have errors. No matter how carefully you do something, in real life, always there is some sort of error, especially when you are measuring things. And if we don't take into account these errors, then we will also get wrong results. I mean, we are bound to get wrong results, but if you do not take into account the error that you are making, then you also do not know how big the error is. It may get so big that your whatever you want to do with all these things, that may get disrupted. Okay, so the smart thing to do, without vainly trying to be perfect, because perfection does not exist actually, especially when we apply mathematics to real world situations, errors will creep in no matter what. So the smart thing is to take into account those errors and try to minimize the error. That is the thing we can do. So that's why now the question is this. Again, you see, again you have a function. There you had 2x minus 1. here the function is 36 by h. Here the independent variable is h and the dependent variable is the function or the volume. So now we need to know this. We want this. V is the actual volume of the water that we have poured. We want V to be close to 1 liter or 1000 cubic centimeter in such a way that this difference is not more than 1% or less than or equal to 10 cubic centimeter. We should maintain the sameness of the units. Okay, if we have different units, then we will, it's a mess up. We want this to happen. And now the question is, how can we make this happen by controlling h in that sense, in the sense of the previous example. So let's see, again we have an inequality. So first of all, we use the expression for V. That means we have this. We have this means we need this to happen. But what do we have to do for that? Okay, so now that inequality, again like before, is equivalent to these inequalities. Now we add 1000 throughout to all the terms available here, then this will be 1000 minus 10 is 990. And this will be 1010. And now in order to isolate h, we divide throughout by 36 pi, which is a positive real number, so the inequalities don't change direction, they stay in the same direction. And now in order to get an actual value, what the author has done, has calculated well, and this is where I should not use this, I should only use implies. Okay, or should I? Actually, let me just first write the values down and then I will say what this part is. It is a little different. You see, starting from this requirement, that is we want this to happen, up to these inequalities, we have had equivalence. Okay, having this inequality is equivalent to having these inequalities. However, we want this, right? So we can assume this, and from there you can go back because you have equivalence and have this that you wanted to have. However, this is not actually exactly equal to 8.8. So what the author has done is that it is in fact a little less than 8.8. So instead of considering that value, the authors have simply taken 8.8 here. Why? Because if your h is greater than or equal to 8.8, then age is automatically also greater than or equal to this, because this value is a little on that side of 8.8. Similarly, this value 1010 divided by 36 pi is a little greater than 8.9. So to be safe, the authors have taken 8.9 here, so that if your age is less than or equal to this, then age is automatically less than or equal to that slightly larger value. And from these inequalities, you automatically have these inequalities, and that's how you have this. However, this actually does not imply this, so instead I should write this. From here you can go to these inequalities, but from there you cannot come to this, not necessarily, unless your age actually satisfies these things. But anyway, that's what we want, right? We are not choosing v first. Age is our independent variable, so we need to choose age first, and then for that age we will have v, which will satisfy some inequality. But because we want to know how to choose age, that's why we are doing this kind of back calculation, okay, reverse calculation. So this is how age needs to be, age should satisfy these inequalities. If it does, then only the volume, the actual volume of your liquid and the 1 liter volume, the difference will be not more than 10 cubic centimeter or 1% of 1 liter. That's why you have a little room for making error, which anyhow you are bound to make, no matter how carefully you are pouring the thing. And the thing is that the difference between these two values is 0.1, and what is our unit? Centimeter. That is equal to 1 millimeter. So that's why between those markings, if there is a 1 millimeter gap, then even if you make some mistake, now say this marking in the middle of these 3 lines that you see here, this is, say, it's denoting the height 8.8 centimeter, and the marking above that is 8.9 centimeter. So if you somehow keep your water level between these two markings, then you can achieve this. Then your actual volume is close to 1000 in this sense. The error is not more than 1%, it's less than or equal to 1% of 1 liter or 10 cubic centimeter. Now, with these two examples, let us see something else, more general, about general functions. These two examples, of course, are special functions, two example functions, where we try to keep the output controlled in the sense that it becomes close to our intended value. How close, that is also specified. For that, what is it that we have to do with the input values? They need to be close to something. How close? That is something of an answer to a challenge. This is a kind of challenge that someone is throwing at us. So someone challenges us, can you make V close to 1000 in such a way that this inequality is true? Is it possible? Answer me. Our response is yes, it is possible. If we keep age within this interval, then that is possible. So it's a kind of a competition in which you have challenges and then you are responding to those challenges. The challenges come and they become different challenges by changing this error tolerance. Okay, how much error can you make? Someone may challenge you to make this difference even smaller, say less than or equal to 1 cubic centimeter also. If you are able to produce for that challenge also some kind of response like this, then you have won that challenge. Okay. For a given challenge value here, you may or may not have a response. But let us now see this idea more generally. More generally means, let us see now the actual most general case of a limit. Suppose you have a function like this, whose limit as x approaches x naught is a real number L. Okay. And vaguely, how do we express it? I mean, what do we say? We say that as x approaches x naught, f of x approaches L, or as x is close to x naught, f of x is close to L. But now comes that thing, how close? So someone challenges us like this. It's best to understand these things geometrically first and then go to equations or inequalities, whatever they are. Suppose this is the graph of the function f, that is, it's the graph of the equation y equal to f of x, and say x naught is this point. Okay. Now, do you see the similarity between this situation and the graph that we drew for example 1? In example 1, actually that other point 7 was the value of the function at the point 4. Here, however, that is not necessary. Okay. F may not have a value at x naught at all. Think of this as this function, where x naught is 0. At 0 there, this function is not defined. However, you still have a value of the limit of this function, that is 1. So that 1 is this L. Okay, so this L is not necessarily f of x naught. F of x naught actually may not exist. Think of it that way. Now, the challenge that the challenger poses is this. Is it possible to do, have this inequality? For that to happen, what you do, you just mark out these places such that this point, this number above L is L plus 1 over 10, and this one below L is L minus 1 over 10, so that this inequality, having this inequality, is equivalent to having the f of x values within this interval, so that their distances from L all are less than 1 over 10. 1 over 10 on that side and 1 over 10 length on this side of L. Now, to make this happen, let us see what we just simply blindly get from the graph itself. So we should be within that strip. That means correspondingly our input value x should be within this interval. Okay. However, we want an interval in which this thing is happening whose middle point is x naught. Now, because the graph is not really symmetric about anything, the graph is just sort of like this. So you can see that the right boundary is a little closer to x naught than the left boundary. So what we can do, we can call this right boundary, this will be x naught plus something, no? Because it lies to the right of x naught. Let us call that something delta. And in order to show that this delta is really coming because of the value 1 over 10, we just put suffix 1 over 10 with delta. So x naught plus delta 1 over 10. And on that side of x naught at an equal distance, equal to this distance, that which is delta 1 over 10, we have this other number, which is x naught minus delta 1 over 10. And you can see that if your x lies within this interval, then of course your f of x will be here within this strip that is here. So clearly the distance between that f of x and L will be less than 1 over 10. Expressed mathematically, we are saying this, that if your the distance between x and x naught is less than this, then the distance between f of x and L is less than 1 over 10. So that 1 over 10 is the challenge from the challenger. Can you make this happen? And your response is this delta. Yes, I can do it. Okay, so you have won this challenge. But then the challenger makes it even more demanding by choosing a smaller value here. Okay. In that case, you may or may not have a response. So the figure will basically be the same. The only difference is that here you will have, say, 1 over 100. Okay, there is no point drawing that figure again, because anyhow we are not measuring actual distances or doing something like that. Suppose you have a suitable response for that challenge also, then this will happen. If the distance, and let that response be accordingly delta 1 over 100. It's a number after all. Okay, we are calling it delta, and to indicate the fact that it depends on that challenge, we are putting the challenge here as suffix. So the challenger keeps challenging you, and you keep coming up with responses like this. And this should be true if this limit has to be true. Why? Because when we write this limit and when we say that the limit exists and is equal to L, then we say that f of x is close to L when x is close to x naught. But the moment someone asks how close, we should be able to answer how close. That is, how close can you make f of x to L? As close as you want. Okay, let me give you an actual value 1 over 10. Can you do that now? Yes. How? By controlling x like this. So I have a response to your challenge. Then the challenger defeated comes back with a new challenge. You give you should be able to give a response to that as well. And this should go on. But this should go on means what? How many times, how many challenges are to be posed and how many of them are to be responded to like this? And the answer is infinitely many. But that just itself sounds quite vague, no? I mean, if you just simply keep on doing this, this will never end. So, what is it that will once and for all make sure that this limit exists? In fact, what does it mean in terms of these challenges and responses? It just simply means this. If the challenger presents a challenge in the form of a number like this, epsilon, which is greater than 0, of course, because after all it represents a distance. It tells you how much the output values can stray from L. For any such epsilon, if you can somehow show theoretically where epsilon is epsilon, okay, epsilon is not some concrete value 1/10 or something, it is any epsilon. If for any such epsilon, there is a response such that this happens, then we say that the limit exists and is L. So the quantification of how close is done by this epsilon and delta. For every epsilon challenge, there should be a delta response, and this has to be shown without attributing any special value to epsilon or anything. Epsilon is just simply a positive real number, that's it. You should be able to show that for any positive real number epsilon, there is a positive real number delta such that this happens in this form itself. That proves that the limit exists and is equal to L, because it's a limiting process, and for functions like this, which actually do not even have a value at that point, you cannot establish that the limit exists simply by putting some, say, 100 or 500 values. No, you have to do it infinitely many times in this sense. Okay, so that's the thing. That is in fact the formal definition of limits, and the definition actually is given like this. It's given as a proper definition. So let's just see what it's going to be. Just this, but there are some other things to be said. Let f of x be a function defined on an interval containing x naught. Containing x naught except possibly at x naught itself. Okay, and one such example is that sin x over x, which is defined in an interval containing 0, but the function itself is not defined at 0. It may or may not be defined at 0. That's why we say that except possibly at x naught itself, it is defined in an interval containing x naught. Also, x naught the interval over which f is defined and contains x naught may not have x naught as its midpoint. That is not necessary, it just contains x naught. We say that f of x approaches a real number L or has L as its limit as x approaches x naught. Perhaps I should write it in words as x approaches x naught and write in symbols like that limit of f of x as x approaches x naught is equal to L if for every challenge, every real number epsilon greater than 0, there exists some real number delta greater than 0, a response such that these inequalities imply this inequality. The reason for taking this to be greater than 0 is that we are not assuming the, we are not taking the value x equal to x naught in this situation. That's because f may not be defined at x naught, and in fact, actually I should have mentioned this in those examples itself. That's because the fact that L is the limit of f at x naught has nothing to do with what happens at x naught, but what happens around x naught. So that's why we are discarding the case x equal to x naught. That is equivalent to having this a positive real number. It can either be positive or 0. So we have removed the possibility of it being 0. Okay, so x is not, in other words, instead of writing this, you can write this less than delta and x not equal to x naught. That's it, that's just what it means. Then this happens. If this condition is met, then we say that the limit of f at x naught exists and is equal to L. And that's just it, that is the actual definition of the limit of a function. These Greek letters have been chosen to represent some things. For example, epsilon is actually Greek E. It represents error. And delta, I think it represents difference. That's just it, because delta is Greek D. So let me just end the video here itself. We now know precisely what limit is. This is the actual definition of the limit of a function. Now we are going to illustrate this definition in some examples that we will do in the next calculus update. And then using this rigorous definition we will actually prove theorems on limit. And then we will see after that what comes. And this definition was given by Karl Weierstrass, which actually came much later than the time when Newton and Leibniz developed calculus. In fact, they did not have this rigorous definition. They did their work with limits in much the same way we handled limits in the previous section. That is, intuitively whatever we feel the limit should be, they also calculated limits in that way, and sometimes that resulted in errors also. But anyway, now we know the actual definition, and so we will take advantage of this and see in the next update what comes next. And with this rigorous actual definition, we can in fact prove things about limits without any doubt and with absolute rigor. And that's just it for tonight. Tomorrow again we have an update. I can't remember whether tomorrow we should solve ring theory problems or group theory problems from Galilean. I don't remember. Whatever it is, you will see it. And because it's problem solution, so it will appear as a community post and not as a video. Okay. So with that, I just sign up for tonight. So see you tomorrow in community posts. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.